Hello, everyone. My name is Joshua Olusegun Ajitomobi, and it's my pleasure to welcome every one of us to this month of August basic econometric class. It is a free webinar that holds every month in the second Friday of every month, or second Friday of every month. So it's my pleasure to welcome every one of us to this month's edition. This month, we shall be considering model selection and validation. And for some that are peradventure joining us for the first time, please be advised to go to my YouTube. You can just go to Google, type Joshua Olusegun Ajitomobi YouTube channel, and subscribe to my YouTube channel. You have several econometric classes that we've held. You can go through them. It's absolutely free. And please feel free to invite your friends, your students, your colleagues, policymakers, practitioners, or those that are interested in econometrics so that we continue to rub mind together on basic econometrics analysis. So again, I welcome you to today's edition. And like I said, today we want to consider model selection and validation. So by way of introduction, we already know that our regression analysis is normally used to look at relationship between dependent variable and independent variables. And when we are dealing with two variables, as we have learned in the past, then there's simple regression, where we have just one dependent and one independent. And in the situation where we have one dependent and more than one independent variables, then we are talking of multiple regression. In social science and economic research, selection and validation of regression models are very essential to ensure credibility, reliability, and generalizability of our results. Usually, we run several models. For example, in our last class, we look at various functional forms. So we can run linear, log linear, a linear log, double log, exponential, all manner of various model transformation methods. And definitely at the end of the day, we cannot base our policy recommendation on all of them. We have to find a way to get our preferred model. Sometimes we formulate our models based on variables selected to be in the model. Take, for instance, if I'm considering the relationship between employment and GNP, for instance. So I want to look at how income generated by a country will affect the level of employment. I can start with something like very simple model that's just relationship between number employed and the GNP. But I know number of employed are affected by more than GNP. So I will have to add other covariates. So in adding various other covariates, even in linear model, I'm already generating a series of models. And at the end of the day, I will still have to look at preferred models based on some criteria. And this is what we'll be considering in this class. So selection addressed the question of what criteria to apply in selecting preferred models, while validation tests the generalization ability of the model. Usually because of financial constraint, time constraint, and several other constraints, most of the time we don't have the capacity to cover the entire population. So most of the time we base our policy implication from sample of the population that uh, we have interviewed or that we have access to the secondary information. So, but still, we want to generalize our research to the entire data, to the entire population. So, in trying to do that, we have what is called validation, and we have various criteria to do so. Shall be constrained in that. So this class covers various model selection and validation criteria, and we will provide, as usual, the R codes for implementing the various methods. Still emphasizing on differences between model selection and validation, let's run through the basic econometric processes econometric process that we normally encounter whenever we are conducting any econometric study. The starting point is to collect the data. And after collecting the data, normally I advise that we should never run our regression based on the raw data. We don't do that. We run our regression on what is called consistent data. And to move your data from raw data to consistent data, then you have to do some cleaning, pre-processing, validation, splitting your data into trained data, test data, and carrying out some kind of validation. So at the end of the day, the output will be the prepared data set. So in which case we have the trained data, then we have the test data. Then after preparing our data, then we build the model using different algorithms. So, and just like what I've said, we can have multiple candidate models, out of which we shall select the preferred one upon which we shall base our policy recommendations. Then after building the model, we select that issues the best model. Then we validate the model, we test for generalization of the results. Then we deploy the model. That is, we put the model into use, integrate it into our decision-making system, and make predictions or decision based on the model that we have fitted. Then the final aspect is model monitoring. We track and revalidate over time because our data do sometimes change, and we have to incorporate the change by tracking and revalidating. So today we'll be looking at model selection and validation. So the process of model selection begins actually with understanding of our research objectives and the nature of the variables that we are using. For instance, if our dependent variable is continuous and we are interested in linear relationship, then the ordinary least square regression should be the base model and often the preferred method anyway. But if our dependent variable is categorical or count-based, then we try the alternative models because if you run the ordinary least square, we end up having bias estimates. So we will rely on discrete choice models, which we are going to begin to consider, God willing, by September. So we'll be looking at some models, logistic, multinomial, passing, all sort of things. So, and no matter the model we use, if we can run OLS on series of models, can use logistic on series of models, and so on and so forth. But as long as we have more than one model, then we have to get preferred model using certain selection criteria. Generally, the selection criteria can be grouped into three. We have the information-based selection criteria, we have the error-based, and the validation-based criteria. For information-based selection criteria, we have archaic information criteria, very good for predictive accuracy. We have the corrected archaic criteria. You can look at the formula. L stands for log likelihood, and K is the number of parameter. Anywhere we find N, that is number of observation. And for corrected AIC, is very, very useful when we are dealing with small sample data sets, so particularly when our sample size is less than 40. Then we have the Bayesian information criteria, the BIC. When our interest is model parsimony, that is, we are interested in getting the simplest model that actually explains the relationship. Then we have the Anaquin criterion. When we are dealing with large samples, it actually penalizes between the AIC and the BIC. For error-based criteria, we have the mean square error. It is the average square difference between the predicted and the observed values. And it's very sensitive to outliers. So we have the root mean square error, which is easier to interpret than the mean square error. So we have our R squared and the adjusted R squared, which explains the proportion of variance in the dependent variable explained by the independent. So we have the adjusted R squared, which actually account for increasing the number of our explanatory variables. And R squared alone can be misleading. That is why sometimes we have to rely on further error-based or information-based selection criteria. For validation, we have three types. We have the holdout validation, we have k-fold cross validation. For holdout validation, which is the simplest and the fastest, we just split data into train data, test data, and select our model based on the validation set. Then the performance estimate can vary depending on the ratio of train to test data that we use. We have k-fold cross validation. In this case, we partition into k-folds, sometimes 5, 10, depending on your choice. And we train on k-1 folds and validate on the remaining fold. That is just the procedure. It's a more reliable performance estimate, but in terms of computation, it's a bit more demanding. Then we have leave one out cross validation. That's an extreme case of cross validation, where our parameter is equals to the number of observation. That is just providing some basic information about selection and validation criteria. So we move straight away to the practical side. So let me open my R. All right. So let's begin with model selection criteria. We'll be using long-lead data. So long-lead data, for some of us that are not familiar with the data sets, the data come with installation of R, which is part of the built-in data set in R. But you can actually use your own data set, just import your data. If you don't know how to import your data from Excel or Stata or SPSS, then you can watch some of my videos. It's well explained there. So what? Anytime we are using built-in data set, it's very straightforward. Just type data, then the name of the data set, longly. So let's run it. So let's look at the forces observation. Head, longly. So this is the first 6 observations. So we have the GNP deflator, GNP unemployed, and for 6 population year employed. To know details of what they actually mean, you can just type asking question here, then longly. So run it. So you can see this is showing us longly economic regression data. It's a macroeconomic data set which provide a well-known example for a highly collinear regression. So it's a data set with 7 economic variables from 1947 to 1962. The GNP deflator is GNP implicit price deflator using 1954 as the base year. GNP is gross national product. Unemployed is number of unemployed. Armed forces, number of people in the armed forces. Population, non-institutionalized population above or equal to 14 years of age. We have year, which is the year. Then employed is number of people employed. So to quickly remind ourselves of the variables, so there's names, longly, so run it. So here we are, so we have the 7 variables. So let us run a few models. So the next thing is let's get our candidate models. Let us try to, let's model 1, let's fix model 1. So let our model 1 be relationship between people employed. Always check the spelling so that we don't make spelling mistake. As a function of GNP, comma, so we have data equals longly. Let's run it. You may wish to look at the results, that's summary. Model 1. Run. Good. So this is the results. So let's look at model 2 equals LM employed as a function of GNP plus unemployed, that is number of unemployed, comma. So data equals longly. Good. So let's run it. Then let's get model 3. So to save time, we can just copy and paste. So we have model 3. So I just need to add, let's add armed dot forces. Let's bring this down so that I'll be able to see clearly what we're typing. So let's run it. Yeah, beautiful. So we can actually um, get a publication ready regression table. That's the next thing we want to do, so that we have the table in Microsoft Word. So we have a publication already regression table. So to do that, we need library model summary. Run. So then we have model summary. Then you have list. So we have model 1 equals model 1, comma, model 2 equals model 2, comma, model 3, sorry, model 3 equals model 3. Then comma here. So we have stars. That is, I want significant variables to be starred, to put stars there. True. Let's put T. So I can move this up. Fine. So so that we can see the result clearly. Yeah, this here. So to look at the result clearly, so let's run this. Beautiful. So this is the result. The beauty of this result is that you can actually copy from here, from Microsoft Word. Copy. So you have your Microsoft Word. This is what I pasted it here actually. So, okay, I pasted it here. Yeah. So now what is important is what I've highlighted here. We have three models. For first model, we look at the relationship between employed as our dependent variable and GNP. In the second one, GNP and unemployed. In the last one, GNP, unemployed and armed forces. So let's look at our results. So if you want to pick preferred model, you look at the R squared. If you look at the R squared, the one with the highest R squared is 0.985. But since it has more than one variable, so the number of predictors is actually accounted for by R squared adjusted. So this is one. If you look at adjusted R squared, still model 3 is preferred. If you look at the AIC, you select the one with the least AIC value, that is model 3. BIC, the one with the least, that is model 3. Log likelihood, the one with the lowest negative, that is model 3. You look at the root mean square, the one with the least. So if in whichever way you look at it, model 3 is preferred, in which case you want to base your policy recommendation on model 3. That is how it works. So I hope it's very clear. So let's move back to our R. So the next thing we quickly want to consider is now our model validation. So model validation. So we want to consider validation approach. So let's model validation. So we said hold out validation, model validation method. So for hold out, we said we create data partition, then we separate our data into train data set, test data set, then we run the model of train data, then we predict on test. That is just the procedure. And we try to do that for the 3 models before we round up to this class. So we need a package to help us, that is Caret, library Caret. So we set seed for reproducibility purpose 1 to 3. Then we have train underscore index equals create data partition. Create data partition. So say longly, it's our data set, longly dollar. Dollar will give us the list of all the variables, but our interest is our dependent, because that's what we are used to do the partition. Then we have our P equals, that is the probability we want to use, that's 0.7. So we're using 70, 30. That is, our train data set will be 70%, the test will be based on 30% of the data. So that is the kind of resampling. Then we have list equals to false. So let's run this. Good. So now we obtain our train underscore data equals longly our train index, comma, simple. That is our train index, which is 70% of the data is our train data. So we want to obtain the test data. Let's run this. So test underscore data equals longly minus train index, comma, simple. So the 70% is the train data, the 30% is the test data. So let's run it. So, and to be sure it runs, you can just say add train underscore data. You can do that also for the test data, so just to confirm that they are there. So add tests underscore data, that's fine. All right. So the next thing we want to do is to fit the model. So fit the model. So the model. So let's start with our model 1. So we have model 1. Let's call it model 1V because we are dealing with validation now. Equals train. Train is a function in caret. Then don't forget we have employed as a function of GNP, comma. Then you have data equals train data, train data, comma. Then method equals LM, linear model. So you run this. Good. So, and now you make your prediction based on this model V. So the next thing we want to do is predict and evaluate. So predict and evaluate. Good. So let's obtain our y at 1 equals is our prediction. So you predict. So you predict model 1V, comma. Then new data now. So our new data will now be test data. So I run it. Good. So now we obtain the selection criteria. So let's call it P1 equals post resample. Post resample. So we have y at 1, comma. Then we have tests data dollar employed. So that is comparing our prediction with the observed. So run. So we have our P1. So run it again. Good. So this is, so we have the root mean square error, the mean absolute error, and our R square. So we try to do that for the other two. Copy, paste. So in this case, we have model 2V. The only difference in this case is we now add unemployed here. Let me draw this so that I can see what we are doing clearly. So this become y add 2, and this is model 2V. Then we run this. So we have our P2. Then we have our y at 2 here. Then you run. Then we have our P2. So run. Good. So then again, let's paste. So we have model 3V. So for model 3V, we have plus unemployed plus hand dot forces so we run it. So now we have y at 3 based on model 3. Then we have our P3. We have our y at 3. Then we have our P3. So we can C bind to look at the 3 quickly, but you can type it out yourself. It doesn't take time. So we have P1, P2, P3. So good. So if you look at the 3, for instance, based on root mean square error, we have to pick P3. Based on R square, we pick P3. Based on mean absolute error, we pick P3. So model 3 is our preferred model, just like what we had the other time. So this is how to use ODAT validation test in order to determine the preferred model. And in this case, we have considered the resampling. This makes it better. So we can generalize the results. So now the last aspect is, if you don't want to use ODAT validation, we try to use cross validation. Though most of the time, I normally recommend just stick to this because cross validation takes time actually. But it's better. So let's look at cross validation. Cross validation method. So for cross validation, let's see, we call it k-fold. In this case, I think we should start with just 5 folds, and you can practice with 10 folds, whichever fold of you desire. So we have train underscore control. You have to first define the method. So equals train control. It's train control. So we define the method. So method equals to CV. No. CV, comma. The number. So number equals to, let's use 5. That's fine. So run the model. So let's train this linear regression model. Train our linear regression model with, now we're using five-fold CV. So let's start with our model one. So let's get model, let's say model one underscore CV to distinguish it. So equals train. Our dependent variable is employed as a function of GNP, comma, data equals longly, comma. We have method equals LM, method equals LM, method equals LM. Then TR control equals our train control to define the method for us. Train control. Good. So we run this model and let's get model one underscore CV. So you can see 0.55, 0.977, 0.5. You can just maybe write it somewhere. And let us do that for the other two models. So copy, paste. So I have model 2. In this case, I will add unemployed. This will be model 2 for me. So I run this. So you can see, yeah. If I compare model 1 to model 2, I see some difference. MAE for model 2 is less than 0.5. So let's finish it by considering model 3. So paste. So this is model 3. And for model 3, we already know we are adding unemployed, then plus harmed dot forces. Good. So and this will be our model 3. So let's run this. Good. So if you look at model 3, for MAE, model 3 is the preferred. For RMSE, you can go up, you will see that model 3 is also the preferred model, RMSE. Yeah. So for RMSE, you can see, just go up here so we can look at it clearly. So let's look at RMSE first. For model 1 is 557. For model 2 is 56. For model 3 is 42, you can see. So in whichever way you look at it, model 3 is the preferred model. So you can try to do that. For instance, now we run 3 models, one on GNP, the other one on GNP, unemployed, the last one GNP, unemployed, and armed forces. If you like, you can have the same model. You can have the same variables, but you can have them in linear. So maybe linear will be the first model. Log linear may be the second one. Linear log may be the third one. You may have the log law as the fourth one, and so on and so forth. You can have standardized. You can have all kind of. You can have even translog. You can have constant residual substitution. You can have all manner of modeling. So, but it's the same approach when you are trying to select and validate your model. So this is the appropriate thing to do when you are carrying out econometric studies. I quite appreciate our togetherness for today. And like I said earlier, our next class, God willing, will be on second Friday in the month of September. And please, you have my WhatsApp number. You can actually maybe send a kind of message to me so that I can include you in our free webinar group, so that all you can have information, you can have this video, you can have other video, you can ask questions, and you can send your questions. We try to ensure that we provide answer to all questions. Then you can have access to this script file so that you can practice on your own. And this is very, very straightforward since we use Longley data set is already built in. And after doing that, you can now maybe try with your own personal data sets. So thank you very much. Your coming, your attendance, I do not take it for granted. I quite appreciate our coming together at all times to brainstorm, to consider some basic econometrics, and to make econometrics simpler than what some people feel the course is. So thank you. God bless you. Till we meet again in September, God willing. Again, I remain Joshua Olusegun Ajitomobi. Thank you very much.